Hi, welcome to today's video. The video is the detailed explanation on how to answer question or assignment number 2, both question 1 and question 2. So let's start by going over the first question. As it states over here with the illustration, the disc shown above spins about the axle at its center. So a student's experiments reveal that while the disc is spinning, friction between the axle and the disc exerts a constant torque on the disc. So what is it all about? So this is the axle. Axle is a stationary part of a wheel mechanism. So it's a system. So wheels, well, of course, the wheel is represented by the disc. So it's an axle. And to give you the scenario, the disc is moving. So the disc is moving while the axle is stationary. So the disc rotates by the axis and the axle, I'm sorry, and the axle is the axis of rotation. So as it rotates like any other contacting surfaces, friction is developed in between them. So friction is always opposite the direction of the disc, and that friction is also called a parasitic phenomena. Parasitic means it reduces the useful work, useful motion. In this case, it's called the useful rotation. So if this is intended to rotate counterclockwise, friction is causing it to slow down. Okay, causing it to slow down. To slow down because friction develops what we call frictional torque, which is the opposite direction of the disk. So here's the first question. At time t equals 0, so the beginning time. So if I am going to highlight beginning time is right here in the bottom. So time also in this graph, it's time t. So that's your time. Has an initial counterclockwise positive angular velocity, omega. So the angular velocity, if it's moving to counterclockwise, so it's positive, omega sub naught. This later comes to rest. So at rest at t equals 1, t equals t sub 1. So rest means it's not moving anymore. So it stopped moving after t sub 1. So this means that at omega sub naught, or omega, I'm sorry, let me erase that one. So omega is equivalent to 0 when t equals 1. Okay, t equals t sub 1. On the grid on the left below, sketch a graph that could represent the disk angular velocity as a function of time t from t equals 0 until the disk comes to rest at time t equals t sub 1. The second requirement on the grid at right below, sketch the disk angular acceleration as a function of time t from t equals 0 until the disk comes to rest at time t equals t sub 1. So first, counterclockwise position. I've already annotated in the bottom. So this is what it meant. So when t equals 0, so that's your x-axis is t, omega is omega sub naught. So that's your dot over there. So you start from there. However, after t equals t sub 1, the disk stop rotating. So now we all know that omega is 0. So let's plot that dot where it says t sub 1 and omega is equal to 0. So by connecting those two dots, you have a slope, a steep slope, starting from omega sub naught all the way to t equals t sub 1, which is 0. Now for the second one, angular acceleration, if we go back and check your reference sheet, acceleration is simply the change in velocity over the change in time. But we're not talking about linear motion. This time it's rotational motion. So it's very simple. All we have to do is change the omega, change the A into alpha, velocity V into omega. So it means this is rotational acceleration, while omega means it's rotational velocity or speed. So now there's your omega. So omega is 0 over here. So what happens? 0 minus omega. So what is the value of our acceleration or our omega? The value of omega is negative because you stop afterwards. So you didn't start from rest, but you end at rest. So that is your final omega or final rotational velocity. So if we go back to our question, rotational, constant torque. So constant torque, what does it mean by constant torque? If we go to Newton's second law of motion, where acceleration is equal to your force or net force, again, it's not force but net force divided by the mass, then we can also associate it with our what we call rotational acceleration alpha. But instead of using force, that will turn into torque, mass into moment of inertia or rotational inertia. So we can plug it in. So the value of omega is also constant. So if the torque is constant, then acceleration is constant. So constant uniform acceleration means it's a horizontal line. But where can we find it? Is it up or bottom of the zero? Since it says over here that it is negative and it is constant, therefore our acceleration is a negative value. But since it is also constant, so it's a horizontal line below our zero axis. Okay, zero axis of angular acceleration. So this is too much to see in a piece of paper. So your solution should only look like this. Oh, there's some more information. The graph is a horizontal line with a negative value. So this is what your solution should be. So in your worksheet or in your answer during the actual test, just draw this line stating what is this value over here, omega 0. Well, actually, you need to put, you must label our dots. So there should be, what's the value of x? T equals 0. And then our omega is omega sub naught. So that will be your value. Right here, we have t equals t sub 1. And then the value of our omega is 0. You can do a shortcut like this, or if you want to be more specific, you can do it on the other side also. Likewise, if we start with time equals 0, our omega, our alpha is alpha, and t sub 1, our acceleration is still the same, and that is alpha as well. Yeah. So these are the only information you need to have in your worksheet. So if we go to the next slide, this will ask for question letter. So question letter B, there are two different solutions that you can use. First of all, using Newton's second law, which is A is the net force over m, but we all know the relationship between linear and angular motion, where A is simply the angular acceleration multiplied by the radius r of a rotating object, and mass is simply our rotational inertia divided by the square of the radius, where It is also known as the point where the axis or the object rotates from its axis of rotation. Let's plug in the variables. So now alpha times r is equal to the summation of forces over I r squared. So manipulate the equation. Now we have I, which is the net force times the square of the radius over alpha, which is acceleration. Now we can cancel our r's, so there's no more r in the denominator, just one remaining r in the numerator. Simplifying it further, but we also know that force, or the net force for that matter, multiplied by r is the torque. So that's the definition of torque. So now we can replace it that I, or moment of inertia, or rotational inertia, is equivalent to the sum of the torque, or the net torque, divided by the acceleration. But if I'm looking at this, it's simple. I can just change my net torque to torque. However, how am I going to use my omega and t sub 1? Oh, so now let's think about the relationship of angular acceleration. So what else can we think about acceleration? Acceleration is simply the change in angular velocity divided by the change in time. So simplifying it further, so let's plug in that value. Now we have delta omega, or the net torque divided by omega, delta omega divided by delta time. So now by using your math skills, you can manipulate the equations further. Delta t over delta omega. So plug in the values specific to the question. So I don't have my omegas and time. So since our torque is simply, the net torque is simply torque because it's constant. So it's a constant torque. So the net torque is the torque itself. T sub 1 minus 0, because the final time is t sub 1. The initial time start from 0. Now for our velocity, angular velocity, we end at 0. We start at omega sub 0, so omega sub naught. So we all know that the difference between these two is negative, so we have a value that is negative. So that's the first solution. You can use the solution, or you can also use the second one. But what if I didn't remember Newton's second law? There's another one using angular impulse. So angular impulse is simply the change in momentum. The change in angular momentum, that's why it's called delta L, is equivalent to, in linear, it's force times delta time, since this is rotational, so that is torque times delta time, or the change in time. But we all know that omega, or I'm not, sorry, not omega, but momentum, angular momentum is simply I, which is your moment of inertia, multiplied by your angular velocity, which is omega. Because impulse is a change in angular momentum, therefore we all know that we are not going to change the inertia unless we change the radius, the rotational inertia, since the mass will remain the same. In this condition, the radius doesn't change because the disk is rigid, or the disk is constant in terms of its radius, or the size of the disk is the same. So the I, or rotational inertia, will not change. However, the angular velocity change from omega sub naught to 0. So let's plug in those variables, coming up that in rotational inertia times the change in omega, or change in angular speed, is equivalent to torque times the change in time. But we all know that we can also manipulate the equation by putting all those deltas together in one side of the equation. So that's omega divided by, or delta omega divided by delta time. But that sounds familiar. Okay? But it's not something that we have to simplify right now. So as you manipulate the equation, now you have torque, which is on this side of the equation. And as you want to move your delta time, so right there, and then u divided by omega. So let's plug in the specific values again. Delta time, you start with t sub 1, which is your final time. And then for your omega angular speed, we start with 0 because that's the end velocity, angular velocity, so that's 0. Simplifying further will give us a negative rotational inertia torque or torque times t over omega. So in the next page, this time, okay, there's some added to this problem, and that is by dripping oil. So again, let's just go over it. So this again has an initial positive angular velocity. So it means same as question number 1. So you start from t sub 0 or t equals 0 and omega sub naught. So it should be at the same dot. Okay. Now, if you read closely to I, subset I, which is the time at which the disk came to rest. So it means that this time it is very specific. This statement made it clear that it did not came to rest for question C. So it will not end at 0 anymore. Okay? It will not end at 0 because of what? Because of the oil. The purpose of the oil is to reduce friction. So as you reduce friction, there's what we call a negligible amount of friction, but friction is still there. So we can overcome that negligible magnitude of friction. So by adding oil, you reduce friction to at a certain point that it is negligible already. So by adding oil, adding lubricant, it reduces friction among those contacting surfaces and thus reducing the parasitic load of friction. So now let's assume that it will not end at 0, but it will end at a dot above 0. So it means it's still moving. Now let's take a look at this. Do you think it will end up as a straight line like this? So it should be a straight line, assuming that's a straight line. Do you think it will end up as a straight line? Of course it's not, because we did not apply oil from the start of t equals 0. We did not start it with oil, but we only apply oil according to the problem. Oil is being added when t equals 1/2 of t sub 1. So halfway the rotation, or halfway the time, oil was added to your system. So let's remove that over here. Something that you need to remember. Since all the conditions are the same as question A for sections t equals 0 to t equals 1/2. So this is where your t equals 1/2 t sub 1. So somewhere within this line, okay, somewhere between this line, within that line, something happened. Oil was added. So the graph should have the same slope as question A. So it should have the same slope that it's going to go straight right here. So you should be thinking of a slope, assuming that's a straight line. Okay, so it should go straight to 0, but it's not the case. So you only have that same, again, let me just draw it again. So you should only have, oops, okay, let me do it again. It should have a straight line all the way to 0, like this. So that's only for the first section. So let me just put it here, somewhere there. It should be this way. Okay, so now let me erase this. Now what happens next? Since the friction was reduced, so therefore the deceleration or how it's slowing down changes also. So now let's connect this dot from t 1/2, t1, to all the way to t sub 1. Since friction is reduced, again, I mentioned it, since friction is reduced, so you will have a less steeper slope, less steep. So now the slope for this section is less steep, but it's not going to be a curve. It's linear graph. Again, I've been reminding everyone it's physics 1, so all your lines should be straight in terms of angular velocity, in terms of velocity, even linear. In terms of acceleration, it should be horizontal lines only. Okay, so uniform accelerated motion. Since there's no more space for the second graph, let's move to the next page. Just use it as our graph. So again, so same condition, just like in number 1. So it's supposed to be decelerating at the same rate. But since you apply oil, what will happen here? So the deceleration will change also, but this time it's a little bit closer. So from a higher negative value to a lower negative value, so it should go up but not go beyond 0 because acceleration is not 0. It's not a uniform motion that the acceleration already reached 0. Instead, there's still deceleration, but the deceleration, according to this, has something to do with the friction that's being reduced. So now your graph is going up, but not to the extent that it reached 0, or it did not reach above 0, or else it will move the opposite direction. So a lot of us has the tendency of doing this. Instead of having the horizontal line, most of you would connect this dot like this. Okay, so uniform accelerated motion, all acceleration should be horizontal line. A horizontal line, so where do they connect? There shouldn't be a smooth slope, but just change it and show this graph. This is how acceleration is graphed. So, next question. That is question letter D. Or let me just specify that this is how your graph should look like in your solution. You don't have to show all the work as indicated in the previous slide. It's just my way to explaining it to you. So letter D, a student is trying to do mathematical model the magnitude torque of the exerted by the angle on the disc when the oil is present at times T is greater than 1/2 of T sub 1. So moving forward, so after 1/2, okay, after 1/2 T sub 1, if you're adding oil, appropriate oil, what happens with the torque? Okay, we all know it will reduce. But which equation will represent that statement? So let's go over here. So what is the scenario that we want to know? Okay, so it should reduce the torque. When you add oil, you reduce the torque, you reduce friction. Lower torque, lower friction because of the oil. So let's take a look at your evidence. So evidence is also part of a qualitative and quantitative analysis. This is where you're graded for question number 1 in your test. Your ability to do qualitative and quantitative analysis. So oil is applied every 1/2 of T sub 1. This means that time is added, or T plus 1/2 T sub 1. So if you subtract, it means it's before T. So it means before 0. It's not going to happen. So since it means that it is added, so therefore it should be plus 1/2 T sub 1. So right away you will say, oh, the solution is number 2 because it says added. you can select equation number 1. But that's not enough because you have to prove the torque. How would you prove that the torque is decreasing? Now here's another one. So frictional torque decreases as oil is applied every 1/2 of T sub 1. If constant C, so either C1 or C2, is multiplied by the increased time, so when you increase the time and you multiply it by C, then the frictional torque increases over time. Also, if you multiply something with a greater number, the torque increases. So if constant C is divided, since it's constant, constant means it's never going to change. For example, if it's 2 divided by whatever number it's increasing. So if constant C is divided by the increase in time, then frictional torque decreases over time because the greater the number over here, the greater the number, the lower the torque is. Over here, if in case this is additive, let's say this one is add, like this. And then you multiply it so it increases. What happens with C? What happens with the torque? If C remains constant, torque will increase also. So that is not possible in terms of the concept that we want to reduce the friction by adding oil. So those are the two evidence that you can use. First of all, T, you add 1/2 T sub 1. So that's your quantitative analysis that it is that equation number 2 is correct. Another one is that you're dividing it instead of multiplying, which is reducing the amount of torque. Again, if you multiply it, you will increase the amount of torque. So reasoning or purpose of applying oil. Simple. The effect of applying oil in between the surfaces of the axle and the disc is to reduce friction, which results in decrease in frictional torque. So we want to reduce frictional torque. So this is my reasoning. And that is the purpose of applying oil. And what is my claim? Equation number 2, blah, 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 is a better mathematical model for the experiment because if oil is applied every 1/2 T sub 1, this means that time needs to be added, or it should be T plus 1/2 T sub 1. Second, since frictional torque decreases as oil is applied, if constant C is multiplied, then it will increase the torque. If C is divided by the increased time, which is T plus 1/2, then frictional torque decreases. This proves that the effect of applying oil in between the surface of the axle and the disc is to reduce the friction, which result in decrease in frictional torque. So you put all those information together in a cohesive paragraph, getting all the points you need in this section of the test. Again, even though you already watched a portion of the solution, you may always pause, go back, and watch it again and see if you miss a portion of the explanation. I think the next one is question number 2, which you already have seen the solution in our tutoring class. Okay, so why is it that in order for a diver to increase the velocity, you must curl up. You must curl up. So here is the solution to this question. Again, why is it that when they're curled up, that's when they spin fast? It's very simple. In a clear, cohesive paragraph length response that may also contain figures and or equations, explain why the athlete's angular speed increases between figure 1 and figure 2, but decreases between figure 2 and figure 3. So this time it's okay to use equation as your justification. There will be some question where they're going to say without using an equation, but here you can use an equation. Okay. So concept, what's the first concept we need to know? That the omega is omega sub naught plus alpha times t. Another concept that we must remember, that momentum, angular momentum is inertia times the omega, or the angular velocity. So what's our claim? It increases from figure 1 to figure 2. But why do you think it changes? It increases. Most of you will think because you jump, you start from nowhere. It is rotation. It has nothing to do about your linear motion this time. So evidence, the angular momentum is conserved. So it means law of conservation of momentum, angular momentum. College board would always give you question about law of conservation. It's either energy, momentum, mass, all of those law of conservation. So it means that the momentum of the person over here is the same as the momentum when it's spinning faster and when it's slowing down. So it's still the same momentum. Momentum, momentum, momentum. But momentum is L. The nice thing about rotation, unlike regular momentum, mass stays the same. But rotational inertia changes. You will be able to change it by using a concept of what we call the rotational axis. So explain over here that in figure 2 the athlete pulls in her arms and legs closer to the point. Okay, so when it says contain figures, make sure to cite specific figure from the question, from the problem. So point of rotation, so the rotational inertia decreases. So the rotational inertia, so I increases when your radius, when you curl up. So if your if your momentum is still the same, remains constant, so in order to compensate the momentum, you must increase your velocity. So that's the law of physics, a law of science. Momentum will stay the same. So if you change your rotational inertia by curling up, reducing the radius, something will increase, and that is your angular angular velocity or angular speed. Going to the next slide. So you put all those information together in a cohesive paragraph. This is how it's going to look like. The angular momentum of the athlete remains constant throughout the dive. So it means, like in your claim, okay? In figure 2, the athlete pulls in her arms and legs closer to the point of rotation. So the rotational inertia decreases because the radius decreases. Since angular momentum is conserved, and angular momentum is simply inertia or rotational inertia multiplied by the angular speed, omega, the angular velocity increases. In figure 3, the athlete extends her arms and legs, increasing the rotational inertia and decreasing the angular velocity. So when something decreases, the other one should increase in order to compensate the law of conservation. So conservation is something that you must stick in your head or have it ready in your notes so that when you take the test, it's open notes. It's going to be easy to recall. So for rubric, how do you think you're going to be graded? So make sure that 1 point. So this is a 7 point question because it's 15 minutes. So 15 minutes is usually 7 points. 25 minutes is usually 12 points. So 1 point, 1 point, 1 point, 1 point. So this is 4 points for section question number 1. So I will not read it to you. Please make sure to read it at your convenience. Make sure remember what needs to be considered when you're asking question. Okay. First of all, what is it all about? Is it law of conservation? Is it something else? Usually, if it's law of conservation of what? For this case, it's angular momentum. Okay. What are some of the things that you need to remember? Okay. Next, what is the equation? Okay. How would you show it? Now, for this last 2 points, It's more of your interpretation and your writing ability to write a cohesive explanation based on science concept. Do not just describe. Stay away from describing the figure. Yes, in this question, you describe the video, I'll describe the figure where the diver curled up to reduce the radius of its rotation, rotational radius, as we call it. That's why the moment of inertia or rotational inertia decreased. So in order to compensate that, you have to increase your angular speed or velocity. So last part of this question is the rotational kinetic energy K sub 2 rotational of the athletic figure 2 greater than or less than or equal to the rotational kinetic energy of number 1? Yes. Okay. Rotational energy is greater, of course, number 1 because it's kinetic. So kinetic is all about motion. So the faster the object is moving, the greater the kinetic energy. So in this case, let's think about momentum again, and then kinetic energy, which is almost similar to your linear kinetic energy. Again, all we have to do is change m to I and v to omega. So our claim, yes, it is greater than rotation number 1. It's only started to rotate. So what's my evidence? Because of omega. Because of omega, of course. Reasoning. So here we go. Put it in equation, but in your test, you will be not using equation. I'm giving you this thought so you can write it on your own. 1/2. So take note of this, that this section over here is also momentum. So what happens when you increase your I? Decrease the I. Okay? So which one will affect? So the question is, what does what factor affects the kinetic energy? So is it when you increase? Because when you open up, okay, so the case here is that the diver, when they're curled up, you decrease your inertia. You decrease the inertia, but you increase the, I'm sorry, not inertia, rotational inertia. You decrease the rotational inertia because you decrease the radius. And what happens with our omega? The omega will then increases. But when you extend your arms, you increase the value of inertia. However, what happens with our velocity? Since the inertia, rotational inertia increases, and we have to maintain the value of our angular momentum, then we have to decrease our angular velocity. So there is an increase in angular velocity and a decrease in rotational inertia. In terms of rotational energy, the decrease in I does not compensate. If you look at this one, ladies and gentlemen, I is not exponentially growing, while omega is exponentially growing. So let me remove that and change our highlight color to something else. Let's change it to green. It's like what's going around right now, the reason why we're at home. The virus exponentially grows. Okay? Since the velocity increases exponentially, the kinetic energy is affected merely by the angular speed. Even though you decrease the angular velocity or angular speed and increase the kinetic energy, it does not affect the kinetic energy that much. So always remember, kinetic means angular velocity. Angular or kinetic means moving. So it's either angular or linear velocity. It is still the velocity that affects it more. And here's the rubric for question B. And that's the end of the solution for this assignment, assignment number 2. And hope you get a lot of knowledge by watching this video, at the same time comparing it with your notes, which is already uploaded in the file that was in a folder that was already shared to you. Again, thank you very much, and hope to hear from you soon if you have any question. Thank you.